a cast steel, يعني such material, a core of cross section of 3 centimeter in diameter, and the mean circumference. The circumference, because it's a circular core, the circumference, so it's the path. The mean circumference is the mean path or the mean length of the flux. The mean circumference of 80 centimeter. The ring is wound with a coil of 600 turns. Firstly, calculate the current required in the coil to produce a flux of 0.5 milliweber in the ring. The second question is, if the second question said if 2 millimeter air gap is created in the ring. So the first question without air gap, and in the second question we are going to add an air gap in this ring. Okay, so the shape of this core is ring. If 2 millimeter air gap is created in the ring, find approximately the air gap flux produced by a current obtained in the first question. Okay. Find the current which will produce the same flux in the air gap as in one. Neglect the fringing and the leakage. And this figure here show a magnetizing curve of such materials. So the first question said we are going to find the current required to produce a flux of 0.5 milliweber. In the second question, after adding an air gap of 2 millimeter, we are going to find a new flux, because when we create an air gap, we are adding a new reluctance to the core. And if we add a new reluctance to the core, the flux will change. Okay, so if the 2 millimeter air gap is created in the ring, find approximately the air gap flux produced by the current obtained in one. So we use the same outlet current and see what is the new flux after adding this air gap. And the question number 3, find the current that required to produce the same flux, which is 0.5 milliweber. So find the current which will produce the same flux in the air gap as in one. Neglect the fringing and the leakage. And we see here in the figure a magnetizing curve of such materials. Okay, let's now start solving this problem. The first question is, okay,
how can you get in? You have to get the
again, but how?
Oh, here you go.
Okay, I found this element. Okay, so the first question is the current required in the coil to produce 0.5 milliweber. Okay. So for finding the current, of course, we are going to use Ampere's law. Let's use the table, the board. So Ampere's law was that. Let's go to the board. So Ampere's law said that Ni, which is, as we said, which is the MMF, equals to HL. Okay, so the current here should be, the current equals to, the current here will be equal to what? The current here will be equals to Okay. So the current, according to Ampere's law, it will be equal to HL over N. Okay. So this is the expression how we can find the current. Okay. So using Ampere's law, the current I equals to HL over N. So L is given, which is the mean circumference, and also the number of turns is given, which is N. We have to find now H, which is the field intensity. So to find H, we need firstly to find B, which is the flux density. So let's go to the board. So here H is the one which is not known. H, of course, is equal to H is equal to mu 0 times mu r times B. Okay, so according to this solution, sorry, I'm distracted a bit. Okay, راحت لي concentration. I'm so sorry. Okay. So here we are gonna find H from B. Okay, and we are gonna use this figure here. So H will not be calculated, but H we are gonna find it from this figure. So we calculate B, and according to this graph, of course the material mentioned is cast steel. We are gonna find the value of H according to B. So let's go back to the board. We are not going to use this expression. Firstly, we need to find B. B from the expression of the flux, of course. B equals to phi over A. Okay, and we are required to achieve a flux of 0.5. So we are going to find the B corresponding to this value of the flux, and B equal to phi over A. A is the cross section, equals to what? Okay, let's go back to the presentation. We have a ring. Okay, we have a ring. With a diameter of 3 centimeters. So the cross section here is circular. Of course, the cross section here is circular. So in order to find the B, we need to find the cross section firstly. So since the diameter is 3, so the radius is 3 over 2, and the surface or the cross section here, the circular cross section, is equal to pi times 3 over 2 square, 10 to the power minus 4, because we have, of course, the unit is centimeter. Then after finding the cross section, we can calculate B, the core flux density. B is equals to phi over A. Phi is given or is required, the required flux. They ask us to achieve a flux of 0.5 milliweber. That's why we add 10 to the power minus 3. And A is equal to 7.07, 10 to the power minus 4. And the core density here, that's required to achieve flux of 0.5, it's 0.707 Tesla. So according to this value, we are going to find we are gonna find the required H, which is the field intensity from the figure. So I do it already, but we can repeat it. So since we have a value of 0.07 Tesla from this graph, okay, and the material here is a cast steel, we can determine the required value of H that achieve a flux of 0.5 milliweber. So maybe in some exercises in exam or in control, I may give you figures like this, which are the magnetizing curve, or may call it a magnetizing characteristic, in order to determine such quantities like B and H. Okay, so here we found the H graphically. We calculate the value of B and we determine H graphically from the magnetizing curve. I hope that this point is clear. Sorry for my beginning, because I was distracted a bit. I think now I feel better. Okay. 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 Some of you are waiting, I know, because I have suspicion with some names. Okay. That's why I didn't add them. Okay, because there are a lot of fake names here. Okay, Bob, Smiley, Noah, Alex. I don't know what is going on here. Okay, thank you. Okay, so as I said, I hope this point is clear, how we can find H or B graphically from the magnetizing curve. Okay. So let's continue our solution. Okay, so in order to find the current required to achieve a flux of 0.5, we use Ampere's law. Of course, I is equal to HL over N. Here, H is the quantity that is not known, or it's not given. So we can determine H graphically from the magnetizing curve after we find B. So B, of course, is known as the flux density, which is phi over A. And phi, the required phi flux is 0.5 times 10 to the power minus 3. And the cross section here is circular, because we have a ring with the diameter. So the cross section is circular. We found it from pi times 3 over 2 square. And the value of core density is 0.707 Tesla. Okay. From figure, after finding B, so H is the value corresponding to B, 0.707, is 675 ampere joule. So now the required current to achieve a flux of 0.5 milliweber is H is 675 times 0.8, which is the length, the mean circumference of the ring, and N is the number of turns, and the current, the required current is 0.9. This is concerning the first question. The second question is, if the air gap, if 2 millimeter air gap is created in this ring. So at the beginning we don't have any air gap. So find approximately the air gap flux produced by the current obtained in one. So we add, so follow me in this point, we add an air gap in our ring. So let's go to the board. let's go to the board. Okay, so let's go to the board. So firstly, we have a ring. Okay, maybe we have a circle here. Okay, okay, we have circle. So we have a ring like this. This is a ring, for example, like this, with a coil, of course. Like this, for example, we have a coil. Let's try to choose another color. This is a coil. And now we add, okay, wait, we are going to use the reluctance. Okay. So we add an air gap of what? Let's see. We are going to add air gap of 2 millimeter in this ring. So here, of course, we save the same current, which is 0.5, the same current, and we add an air gap. Here, after adding an air gap, it's like we add a new resistance. Look, if we try to show the equivalent circuit of this magnetic circuit, of course, we have a source, and we have the first reluctance, which is the reluctance of the core. And after that, we have added the new reluctance or new resistance, which is the reluctance of the air gap. Okay, okay, I will add him. Okay, you know, I stopped adding a new because I see here more than 10 fake names. Okay, Aslami Amina. Okay, group 9. I see about 10 fake names. Okay, that's why I stopped adding them. Okay, so after adding an air gap, as I said, a new reluctance will be added. This is the first reluctance, which is RC, the reluctance of the core, and this is the new reluctance added, which is the reluctance of the air gap. Okay, so let's go back to the solution. So if the 2 millimeter air gap is created in the ring, find approximately the air gap flux produced by the current obtained in one. Take the core reluctance. Okay, so we are going to take the current and the same as mentioned in the first question. So here we need to find the new reluctance of this air gap. So the air gap reluctance is equal to what? The expression of the air gap, of course. Let's go back to the board. So the reluctance equals to what? Equals to the length over mu0, because it's an air gap, times A, which is the cross section. This is the air gap reluctance. Okay. So the air gap reluctance equals to the length of the air gap, Lg, which is 210 to the power minus 3 because it's millimeter, over mu0 4 pi 10 to the power minus 7 times 7.707 10 to the power minus 4, which is the cross section. Okay, and it's equal to 2.25 10 to the power 6. Okay, this is the reluctance. Why we are looking for the reluctance? So this question asks us to find approximately the flux, and according to Ohm's law, as of one for your colleague says, the flux equals to F over the total reluctance. Okay. As Ohm's law. Okay, the flux is equal to F over R total. Okay. So this law, like Ohm's law, which is V over R. Okay, that's why we have to find each reluctance, the reluctance of the core and the reluctance of the air gap. The reluctance of the air gap is Lg, which is the length of the air gap over mu0 times the cross section. Okay, and it's equal to 2.25 10 to the power 6. Okay, so of course the flux we are looking for, it's a total flux, because it's I will show you. Let's go back to the board. This is our magnetic circuit. If the leakage, if the leakage flux is neglected, okay, if the leakage flux here is neglected, so all the flux will be flow here through this core, and it's the same flux in the air gap if we neglect the fringing and the leakage. So the flux we are looking for in the air gap, it's a total flux. Okay, so the total flux equal if the fringing and the, okay, we have question. My classmate Nassim. Okay, Nassim. Bilal Bushmal, I know him. Mohammed, I know him. Shayma. Okay, now I see familiar names. Okay. Okay. So as I said, if the fringing and the leakage are neglected, so the total flux is the same as the air gap flux. Okay, because we have neglected the leakage flux. Okay, so the total flux is equal to the air gap flux. Okay, so the total flux according to the law, which is similar to Ohm's law, equals to F, the MMF over R total. R equals to R total, of course, it's the core reluctance plus the air gap reluctance. So the air gap reluctance, we are going to use the parameters that given in the first question, which is, okay, here the air gap is neglected. I think it cannot be calculated. Maybe it can be measured if we have a way to measure it. So normally it should be given. Okay, the leakage flux. If it's considered, if it's not neglected, it should be given. Okay. We don't have a way to quantify this flux in the air. Okay. So the total reluctance here . Okay, the total reluctance here is equal to the core reluctance plus the air gap reluctance. So to find the core reluctance, as I said, we use the same parameters given in the first question, which is the flux of 0.5 and the MMF 540. And the core reluctance here is 1.08 10 to the power 6, and the total reluctance is equal to the total flux directly. It's the MMF. Why? Because we are using the same current. That's why we have the same MMF over the total reluctance. And the new flux after adding the air gap is 0.162 milliweber. That's why I told you that the air gap always in real magnetic circuits it should be small as much as possible. يعني شوفوا difference تاع flux after adding 2 millimeter after adding 2 millimeter of air gap, how the flux get reduced. Why? Because the reluctance of the core has been increased. And look, the reluctance of the air gap is much greater than the reluctance of the core. Okay. So now, this phenomenon, when I was teaching before I came to Boumerdes, we done it as a lab. Okay, we have a magnetic circuit and the core, and each time we put carton as an air gap, and we see the new current. So in the third question, we're gonna find the new current required to يعني باش نرجعوا الفلكس to 0.5. So this value after adding this value is after adding the air gap. Now we need the new current to achieve 0.5 again. So to find this new current, so to maintain phi air gap equals to 0.5 milliweber, F, which is the MMF, must be equals to, of course, F equal to R total times phi, the required. So always this phi is the required flux, is the required flux, 0.5. So F is equal to 3.3 10 times 10 to the power 6 times 0.5, and the new MMF is 1665 ampere Joule, and the new current required to achieve 0.5 here is, according to Ampere's law, of course, F equals to Ni, and I equals to F over N. So the new current to achieve 0.5 of the flux is 2.775 ampere. So you can see here the effect of adding an air gap in the magnetic circuit. How much the current must be increased, how much the current must be increased to achieve the same flux similar to the case without an air gap. So this is concerning the first exercise. If you have any questions before passing to the next exercise.